Good afternoon. It is so lovely to be here in Melbourne. So when I talk about what I do, I don't usually use the term AI, and that's because that term means different things to different people. So the problem that I've been concerned with is how do we deploy and build autonomous agents that work in this beautiful mess that we call the real world? And I've been working on this problem over the backdrop of the rise of deep learning. And I recently stumbled across this post by a prominent researcher in the field, Andrej Karpathy. And he characterizes deep neural networks not as another tool in the toolbox of a software engineer, but as a brand new paradigm for thinking about how to solve problems in software. And some amazing strides have been made in recent years to solve problems that we didn't think would be solved by machines anytime soon. And so the question on my mind, as he brings this up, is will this get us to the point where this software 2.0 paradigm get us to the point where we can actually deploy these autonomous agents? And the jury is out, but we have kind of a few choice words from some of the luminaries in the field. So this is some quotes from Jeff Hinton, who is one of the godfathers of deep learning. And he says he's quite suspicious of backpropagation in particular, because it requires many, many, many labeled training examples. And he's quite sure, and I think many of us would agree, that is not how we humans learn. Well, and also if you ask Yann LeCun, another godfather of deep learning, he'll say that unsupervised learning, the way that we humans and other biological life forms learn, is really the dark matter of AI. And I think what he means by this is that AI, or the learning that we do, doesn't match how machines learn today. And furthermore, we don't understand it, and yet it makes up most of how we learn. So just like we don't understand dark matter in the universe, we don't really understand unsupervised learning yet. Francois Chollet, one more example, he is author of Keras, which is a deep learning library, very popular. And he's kind of taking this idea even further and saying, I'm not even sure that we've framed the question properly that will lead us down a path of inquiry to develop these intelligent autonomous systems. So pondering all of this, what I kind of realized is that the problem space I've been working on is not actually a 2.0 problem space. It's actually software 3.0. And so the way that I would describe it would be autonomous agents acting in the real world. This could be a physical agent. Maybe it's a robot or a self-driving car, or perhaps it's a virtual agent that manages your cloud deployment, for example. And so the way that I envision them being deployed in the future is you would define the interface between the agent and the world, i.e. its sensors and its actuators. And you would instantiate an agent, and it would learn on the job. And the way that it should learn is through domain expertise from a human, say, mentor, rather than from somebody that's tweaking models. So I very much expect on-the-job learning. The other thing, if we're talking about a hardware system, I believe that we should be able to get away with not having high-end, very, very sophisticated sensory devices. Because if you think about it, us meatware devices, they're actually very low end, right? If you think about the human vision, there's only a very narrow range at which we have high fidelity vision, and the rest of the picture is filled in inside of our brains. And then going forward in terms of the rise of big data, I think that big data will end up becoming experience. So rather than saying how big of a data set can we accumulate, how much experience can we accumulate in an agent? So that's the problem space. And I'm going to, in this talk, boil it down to a canonical question, which is, why don't we have robot butlers in our homes today? Right? This is something that we've been promised for decades, and why is that not a reality? And once we get into that, I'm going to look at, is there another framework that we're not already thinking about that will get us there? So let's talk about our robot a little bit. What is it going to do? So let's go deep into a particular use case, which is you're thirsty, and you want this robot to bring you a beverage. Pretty simple, right? So we'll add some constraints. We're going to assume that the hardware is taken care of. I'm not a hardware person, so that's my assumption there. And we're also going to assume that we're not going to be using rule-based methods. We've been trying for decades, and they don't work, so we're going to focus on learning methods in this talk. OK, so if I had to describe the problem in a very abstract way, the problem that our robot is trying to solve is finding a way, right? Given some goal that the human is happily drinking his or her beverage, the agent needs to navigate a path from where it is to this goal. And it may in fact be literally a path, right, going from your office through the hallway to the kitchen, but it might be a path in very more abstract states of the world, high-level planning, this kind of thing. But in all senses, we're trying to find this path through the states of the world. So what's the interface look like between our agent and the world? It's pretty simple. The agent is making a series of observations, a continuous stream, right? This is not a data set, this is experience. And the agent is generating action, which can affect the state of the world. And there's some challenges, okay? Given that, what are some of the obstacles in place? So the first is the paths that the agent needs to take are not known at the outset. The agent must discover those paths. The second is, just because the agent learned how to do something in one environment, the environment itself can change. You might remodel your house, or maybe you're going to take your robot to your friend's house to show off your cool gadget, right? So paths that used to work don't actually work anymore. And then the other thing is the observations themselves are imperfect and noisy. If you went to Brian's talk on Kalman folding, you would have seen that when you're measuring, say, GPS data, that you're not going to get the same reading every time. It's going to be noisy, and there's going to be uncertainty about it. So how do you take those observations and infer the state of the world based on that? So let's talk about the behavior we want our robot to have. One that often gets overlooked is we need our agent to be able to resolve ambiguity or uncertainty about the world in a purposeful manner. So, for example, if you want your agent to go get you your beverage, it might not know where the beverage is. It might go, well, maybe it's in the kitchen or maybe it's in the dining room. What you don't want it to have it do is start a random grid search and look in the bathroom first, because that just doesn't make any sense, and you won't really get timely results. The other thing that we need our agent to do is pursue multiple goals simultaneously, in parallel. So the high-level goal is get me my beverage, but in order to do that, you need to actually fulfill a number of needs at the lower level. So keep the battery from running out, for example. Keep the agent from running into obstacles or running into the dog. So avoid damage. So other behaviors that we need are the ability to generalize. We want skills, right? We don't want specific things that work only in one situation. So we want the agent to be able to grasp any type of cup, a wine glass or a mug, what have you. We want the agent to be risk sensitive, that is, avoid really bad states. So we don't want it to do something stupid like jump off a balcony if that happens to be the shortest path to its goal. And then finally, we need the agent to recover from adversity. And when I say adversity, I mean situations that it didn't anticipate when it first made its plan. So that could be anything from the cup gets knocked over to the agent decides to walk down the hallway and gets blocked by a pile of laundry. And if the agent's anything like me, instead of going around, it'll forget about getting the cup and just get the laundry and do the laundry and forget about it. OK, so let's get down to how we can tackle this problem. And we're going to look at two approaches. We're first going to start with reinforcement learning, And this is very much a software 2.0 approach. The most popular sort of approach to it is really in deep learning at the moment. And then we're going to talk about active inference, which is a framework that I believe will solve the 3.0 problem. So just to show of hands, how many of you would call yourselves somewhat familiar with reinforcement learning? OK, a few hands. But I'll kind of describe the basics enough that you'll be familiar enough to understand this. So before we dive in, we have to describe this interface, because I just lied to you. Because I said there was an observation and action. But actually, the way that reinforcement learning problems are set up is that there's this additional piece of the interface, which is called a reward. And a reward is really a number. And it's an arbitrary number that measures the goodness of the states of the world. And so as a designer, if you're coming up with your environment for your agent, you want to design a reward function that rewards behaviors that you want it to do. And you want the behavior that maximizes the reward to be doing exactly what you want, because that's all the agent's going to do. It's going to try and maximize the reward through trial and error. It's going to try all these different things, and it's going to figure out what's going to be the most rewarding. So a note here on deep reinforcement learning. This is a very, very cartoonish picture of what it looks like. But essentially, in deep reinforcement learning, there's one or more neural networks inside of the agent. And the basic idea is the observations come in at the bottom, and out at the top come in action. This would be like a video game, up, down, left, right. And there's somewhere in here this policy. It's usually used this symbol pi to describe it, that selects the action that affects the environment, and then the reward comes back after that. So there are many, many ways you might solve this problem with deep neural networks. And at this point, you might be expecting me to start talking about all the different flavors of how you might do that. But I'm not going to do that. I'm going to instead talk about this reward function, because I believe that this is fundamentally limiting our view on the problem and limiting what we can do with these agents. OK, so let's look at an example of how a reward function might be constructed. So this is from a paper in 2015. And the goal was for different bodies, either a humanoid here or say something with or quadruped, learn how to locomote, right? Learn how to move forward as fast as you can. And so in this environment, the reward function is using these kind of internal or hidden states of the world. The velocity forward, how fast the agent is moving, is a big component of the reward. So the faster the agent moves, the more reward it gets. However, you also don't want the agent to put undue forces on its body. So there's this kind of negative reward coming out of impact forces and joint torques. And so at the end of the day, the agent actually learns how to walk or to crawl or to run quite well. So question for all of you guys, if we take this agent that learned how to locomote and put it in our homes, into our robot, would it actually work? Raise your hand if you think this actually would work well. OK, no, one person? Two people? OK. Not very many people think this would work well. So I mean, the question is, why wouldn't it work? Well, if you noticed, you probably did, that this world here is an entirely featureless, flat plane. There's absolutely no obstacles, no dynamics in this world whatsoever. So the first time it encounters even a wall, it's probably not going to go so well. So I can think of just a few adaptations that we want. So if the agent is facing a staircase ahead of it, you don't want it to go as fast as it can. You want it to actually lift its knees. If it's carrying your glass of water, maybe it's going to be a little bit more careful or even needs to kind of counterbalance the weight. If a predator appears, I don't know, anybody have a 2-year-old in their house? You might want the robot to run away from that. So these are just a few adaptations that I came up with off the top of my head. And so the question is, well, how would we make all of that fit into the reward function so that the agent does the right thing? Well, one thing we could do is like add more inputs to the reward function. I don't exactly know how you would do this, but let's say we could do it. You would add terrain features, you'd add the other actors, you would add predators, right? All this kind of good stuff. And depending on what immediate environment the agent is in, there might be more or fewer of these different features. So that's a pretty high-dimensional problem. So that's one problem. The other problem is if we could come up with a hypothesis of what we think would generate the right behavior, the only way to find out is through trial and error. We need to train the agent from scratch, which could take hours, or days even on many machines. So that's quite expensive. And then finally, what if we get our agent into its real environment and we come up with a particular context that we just didn't think of, right? It's a model. Models are imperfect. And so I don't know about you, but to me, this is starting to feel a lot like the early days of computer vision, where it was all about feature engineering. That's a very laborious process. And so I don't want to get into feature engineering my reward function. Now, there is an active area of research that's called inverse reinforcement learning. And the aim of that is actually based on human demonstrations to infer what the reward function might be. There's a lot of open questions to that. One of the questions is, if you could do that in an efficient manner, how would you kind of get this notion of skills separated? We need our agent to be able to, grasp different objects. We need it to be able to navigate. We need it to be able to locomote and do those things at the right time. So assuming we got all of these kind of skills learned, how do you actually decide when to employ which skill? I mean, do we have one reward function per skill? The other problem is we're talking about neural networks that are trained using backpropagation. And the way that backpropagation works is you propagate this error back through the network and tweak every single parameter by a small amount on each trial, which means you're forgetting something. So if you're trying to learn a new skill, forgetting what you already knew is not a good strategy. So human beings and biological organisms in general, we do something different. We build structure in order to represent new skills. So, I mean, there's still a number of unanswered questions here. Okay, here's another dimension to it, which is this trade-off between exploration versus exploitation. This is important. Exploring is necessary because it helps gain information to improve our model, which improves our ability to predict reward in the future. And so the information that you gain through exploration is known as epistemic value. And you need to do that at the right time. The problem is that reward functions don't include epistemic value. So what do? Well, you got to add something on top of that. So there's many methods. One of the most popular ones right now is called epsilon greedy. And this method essentially entails coming up with a parameter epsilon between 0 and 1, and that is the probability of performing a random action on any given time step. So this is from the Atari DeepMind paper of 2015, the famous one where they solved the Atari video games, and they chose to start epsilon at 1, and then gradually over 1 million time steps, move it down to 0.1, so every 10 time steps you're exploring, and then kind of level out from there. Okay, what's wrong with this? Again, we don't have inherent value in exploration, and the problem is then that we don't get purposeful exploration. We get random exploration. And why haven't we heard more about this problem is that most of the experiments that you're seeing in reinforcement learning are happening in virtual environments in which it's completely acceptable to die millions of times or even thousands or millions of times before learning something. If you're talking about an agent operating in the real world, how acceptable is it to die many, many times? So while this might converge, it doesn't converge fast enough for real world situations. So we might get an agent that explores when it's about to die, and that's not good. The other problem, though, is that once you deploy the agent into its environment, there's no reason for it to start exploring again. So if the world changes at this point, it moves into a new environment, how do you make it explore? Okay, so there's definitely some big open questions here. And I want to end this section with another question, which is, what if the agent generated its own reward? And what if, in fact, that reward included an imperative to explore, this epistemic value? And that brings me to active inference. So at this point, we're going to take a deep breath, because we're going to forget everything that we just learned about reinforcement learning. This is a different way of thinking about the problem, a paradigm shift, but I think you'll find some familiar concepts in here as well. So in order to introduce active inference, I need to tell you a little bit about the free energy principle. And this is the work of Professor Carl Friston out of University College London. And Carl Friston is a rather famous neuroscientist who came up with this breakthrough method of statistical mapping for fMRIs. So he's not really well known in the machine learning community, but he realized as he developed this method that he was actually describing an organizing principle for intelligent life. Now that sounds pretty big, doesn't it? What does that actually mean? So he's used this principle to describe many emergent behaviors or phenomena in biological life, and now he's taken that and described in very precise mathematical detail this framework called active inference that would allow you to implement an agent that minimizes this quantity called free energy, and we'll get to why that's important in a minute. But first, why am I excited about the free energy principle? The reason is that all of these behaviors that I described in the beginning about what we want our robot to do emerge by virtue of this principle. The other thing is that it has many ties to well-known concepts. So if you're familiar with, Bayesian methods, variational inference, statistical physics, information theory, and in fact, under certain assumptions, the Markov decision process, which is the underlying process or description of reinforcement learning problems, can be posed as a special case of active inference. So it's pretty exciting. Let's get into some intuition about how this principle works. So you go to the store and you get an egg. It's just an ordinary unfertilized egg. And you're hungry, so you want some breakfast, so you get out your spatula and you scramble the egg. And during this time, the egg goes through this kind of irreversible transition from a state of wholeness to a state of scrambledness. And this is kind of one way to describe the second law of thermodynamics, because the probability of the molecules in this egg sort of spontaneously reforming to be this whole egg is infinitesimally small. And this is kind of how we describe entropy or disorder increasing in the universe as time goes on. Okay, so what if we had a special egg? And this egg had a face, and it had a pair of legs. And this time it sees the spatula coming, and it runs away. So what did this egg do? It avoided crossing this boundary here. It stayed in this good state that is compatible with its own behavior because it can not only sense but act upon the environment. So to zoom out at the 30,000 foot view, we have intelligent agents maintaining very narrow sets of states to more or less, for at least temporarily, defy the second law of thermodynamics, defy all of these dispersion forces acting upon us, right? We stay in a warm room to stay warm, right? We eat food to keep our systems running nicely. So we're acting on the world to maintain this very small set of states, and a very obvious kind of result of that statement is that these states are preferred by the agent. So one point about that, which is that preferred is in the eye of the beholder. We have an environment here containing two agents, one of which is in a very, very preferred state, and the other which is really in a dead state. So the states that you would find fish and birds in are quite different. And when you really think about that, you start to wonder, how much sense does it really make to pose the problem in such a way that it requires a reward function coming from the environment? I mean, isn't this more of a property of the agent itself? And that brings me to the free energy principle, which is essentially inversion of what I just said. States that are incompatible with your survival are those very states that are surprising or improbable. Surprising meaning you didn't expect them. And so intelligent agents need to minimize surprise. And I mean a very specific thing when I say surprise. What does this actually mean? If you're kind of familiar with Bayes' theorem, surprise is essentially this curve, this negative log probability of being in some state given your model of the world. And so if you're at probability 0, that is, you don't expect to be in the state, your surprise is essentially infinite. Whereas if you're at probability 1, like you believe the world is completely static, then your surprise is 0. The problem with surprise is we can't actually measure it, because it requires knowledge of hidden states of the world to which we don't have access. Fortunately, we can define this quantity called free energy, which is an upper bound for surprise, because it includes this kind of divergence term that's non-negative, that is this difference between what states you expect to be in and what your sensors are telling you you're in. And so the smaller you can make this divergence, the better you estimate your surprise, the more intelligent you become. So I keep using the word model over and over again, because we all need to build a model of the world in order to do this. So this particular formulation of free energy includes both a complexity term and an accuracy term. So we minimize free energy not just on one level, we actually minimize it on several levels. We minimize it on our perceptions of the world, which are hypotheses about the world. These can actually vary moment to moment. We also minimize the free energy on our policies. These are paths through the states of the world. This is the dynamics of the world. We have a predictive model that predicts how the world evolves. And then finally, we minimize free energy on the model itself, on not only the parameters of the model, but the structures of the models as well. And the best way I could probably think of to give you an intuition about this is raise your hand if you're familiar with the concept of overfitting in machine learning. Okay, a few people. Okay, so the basic idea is when you're training a neural network, you're giving it a training data set. And it's possible, if you give your neural network enough parameters, to get 100% accuracy on that training data set. The problem is the resulting kind of nonlinear function that your neural network is approximating is incredibly complex, which means your model is not able to generalize well. If you give the model some new data it's never seen, it's probably going to give you some answer that doesn't make any sense. So in machine learning, what you would do is you would start to introduce regularization, and that more or less reduces the complexity of this nonlinear function. So when you're minimizing free energy on a model, what you automatically get is kind of this maximization of accuracy while minimizing your complexity of the model. And that allows you to generalize, to be able to learn skills like holding different types of cups, separating the notion of what versus where. So let's go into active inference. and sort of compare that to reinforcement learning. So the idea is, in active inference, there is no such thing as a reward function coming between the agent and the environment. Instead, the reward is intrinsic in this model by virtue of minimizing free energy. And we can actually implement free energy minimization under a framework known as predictive coding. And the currency of that model is prediction error, right? So predictions come from above, from high level to low level. They form your hypotheses or perceptions about the world. And any kind of mismatch between that and your sensory observations creates prediction error, which you can think of as free energy. So the goal is minimize your prediction error. Okay, so one thing that's really fascinating about the act of predicting, right? This is a predictive hierarchical model of the world. You're trying to anticipate what your next sensation is going to be. And prediction actually under active inference does two things. The first thing is it's forming perceptions. So if what you're seeing doesn't match what you believe you're seeing, you can adjust your beliefs or your perceptions about what you're looking at. But you can also, given some prediction, change the world to make your prediction come true. So when the predictions reach all the way down to the sensory level, and in particular I'm talking about these sensors called proprioceptive sensors, these are attached to your actuators, you can actually make them come true. So just by way of example, I see my finger out in front of my face, and I predict I'm going to sense that my arm is actually touching my finger here, and my nervous system makes that true. So this is a pretty profound simplification of a number of problems in reinforcement learning that I unfortunately don't have time to do justice to, but I wanted to point it out while we're here in case you're curious to learn more. Let's get back to our robot. Okay, so if we first need to describe what it is we want our robot to do, we need to give it some kind of goals. And earlier I talked about this notion of states compatible with survival are those that are preferred. So we need to define preferences. There's a couple places where you might get preferences. One is the experience of your ancestors. What states were they in? And you get those passed down through your genome. But another way you can get preferences is through your experience. As you experience life, you start to prefer the states that you most occupy. But we're talking about an artificial agent, so we don't have to wait for evolution. We can actually tell the agent what it prefers when it's appropriate. So we can say, you prefer this high battery. And so again, this is really a probability distribution. It's not like a single number, but it's saying, hey, given my model, I prefer to be in this state. And the beauty of this formulation of preferences is that it's completely independent of the environment. That is, it doesn't say, in this environment you prefer this, in this environment you prefer that. What it's saying is, whatever environment you're in, figure out how to get there. The other thing about preferences is that they can be high dimensional. Battery level is one thing for an agent, but avoiding damage would be yet another level. And keeping the human happy would be yet another. You might have a big red button that says, hey, I'm happy or I'm not happy, right? As giving feedback there. So given that we have this hierarchical predictive model of the world, we can actually balance across all of these different goals or needs simultaneously, right? This model works in parallel. And when these guys are competing, we can actually do kind of a cost-sensitive prioritization across these different preferences. Let's get back to this kind of notion of finding a way, getting from where you are to your goal. An agent that implements active inference learns policies, which are essentially paths through the states of the world. And it has a memory, right? So it knows kind of, here I am now, here's where I was recently, and here's where I expect to be. And because where I expect to be includes the goal, that's a good thing. Let's look at a couple of scenarios for how this plays out and how we get the behavior we're looking for here. The first is overcoming adversity. So the robot's in the kitchen, it knocks over the cup, or maybe the cat knocked it over, and it has to recover from that. So in this case, let's say the robot chose a policy to get it to its goal, which was make the human happy, and it predicted it was going to be in this state where it was looking at its hand holding the cup. But instead, where it found itself was actually the cup is knocked over. So this formulation of free energy, this is free energy minimized across a path, includes this kind of complexity term, which becomes very high when the observations don't match what the policy predicts. Which means this policy that it was following becomes totally improbable. It stops performing that policy and instead chooses this other one, which now aligns well with where it's at and the goal as well. So let's talk about risk sensitivity. The previous slide, I was talking about this quantity free energy, which is kind of this paths through the states. And this one, I'm going to talk briefly about this quantity called expected free energy, which is very much related, but it is evaluated with respect to outcomes, and in particular, these preferred outcomes. So if there's sort of a high difference between where the policy predicts the agent's going to go and where the preferences are, it's going to say, that's too high of a cost, that's too high of a risk, I'm not going to do that. So in this case, there's two possible paths to the goal, one of which involves, let's say, climbing over an obstacle, which means, oh my God, my battery's going to drain. And so this one has high expected free energy because this cost of the state is just so incredibly high. Whereas this path involves going around, and the cost is much lower, so the agent chooses this path instead. Okay, and finally, let's talk briefly about ambiguity resolution. If the agent is uncertain about the state of the world, it can actually resolve that in a very purposeful way. So in this case, the agent has reached the kitchen door in trying to bring you the beverage, but it doesn't yet know what's the state of the kitchen going to be. Is the cup going to be on the counter, or is the cup going to be not on the counter? So if you look at these states as a probability distribution, maybe this would be 50% and maybe that would be 50%. But in terms of the next step to resolve that ambiguity, either way, it needs to open the kitchen door. So it's going to open the kitchen door, and then you'll either see close to 100% this state or 100% that state, and then the path it's going to take will become very, very clear. So this expected ambiguity, although it doesn't know where it's going to be now, is actually low because it expects I'm going to resolve my uncertainty about the world by opening the kitchen door. And then finally, I just want to point out another kind of rearrangement of expected free energy. If we take the negative of that, we get value, right? This is how valuable is a particular policy. And if we rearrange it, we exactly get extrinsic and behavior, extrinsic value, and epistemic value. So by nature, agents that minimize free energy explore naturally, and they balance these two things out naturally. So my conclusion here is that if we implement agents under active inference, we're going to get these emerging behaviors that really describe intelligent life, but more importantly for us, get us the robot butlers that we want. And we also don't have to solve all these problems around reward coming from the environment. Finally, by nature, our agent is going to be an explorer. So just to kind of wrap up, why don't we have these robot butlers in our house? I believe it's because we're investing most of our efforts toward a framework that leaves a lot of open questions, that doesn't allow these behaviors to emerge, and that would be reinforcement learning. So I think that we need a new framework, and I'm pretty convinced at this point that active inference is that framework. So I hope that I've made you curious about active inference, because I've been working on this problem for the past couple of years. I'm really excited to continue, and I think we need more minds on it. So I'd love to hear your thoughts about this. I'll be around, so thank you very much. And finally, I mentioned a lot of, sort of papers and blog posts and so forth. So if you go to my GitHub page here, I put a whole bunch of links on there to give you all the details surrounding this. So thank you very much. Appreciate your time.